Hello everyone, Assalamu alaikum, and have a good day. My name is Furqan Raza. I am a geotechnologist at Basic Fram Lab Asia. And thank you for being a part of this webinar. I'm going to present today how we can use artificial intelligence to predict the hydrocarbon using well log data. So let's begin. Thank you very much. So I'm going to present you today how we are using artificial intelligence to predict hydrocarbon using the well log data. Using this technology, we can maximize the value by predicting hydrocarbon very efficiently, and while minimizing cost, because we will use the raw data to predict the hydrocarbon. In today's session, we will give the introduction about hydrocarbon detection and how we conventionally detect potential hydrocarbon reservoir. Then we will see how artificial intelligence we are using to predict the same flags in much lesser time. We will talk about the technologies and techniques and the data we are using for hydrocarbon prediction, and at the end we will share our other experience in data science other than this artificial intelligence for hydrocarbon prediction. So conventionally, hydrocarbon detection is one of the activity that we petrophysicists do using the well logs, and we perform this evaluation. We perform this evaluation using two different methods. One is the qualitative well evaluation. The other one is quantitative well evaluation. In qualitative well evaluation, we rely on the visual signals. We do not perform any computation. In this methodology, we look at the GR cutoffs to separate reservoirs from the non-reservoir. And we also look for the GR and SP crossover. We use density neutron overlays to identify the wet zones. And finally, we use the resistivity value to cut off regardless of the classification of the reservoir. So most of this activity is visual, whereas for the quantitative well evaluation, we use several algorithms. Again, the choice of the algorithms are range very widely. Many petrophysicists also use their own algorithms, and there are standard procedure as well. But in this quantitative well evaluation, we use raw logs to determine to produce the intermediate interpretation, such as shale volume, porosity, and well saturation curves. And using that curves, we perform the quantitative well evaluations. So here is an example of how the qualitative evaluation is performed. On the right-hand side, we have a well data, and it's several logs. We have Cali log, SP log, and density and resistivity logs. And on the right-hand side, we have the flags to mark which depth representing can have a potential hydrocarbons. If you notice in this picture, we have marked 7 zones, 1, 2, 3, 4, 5, 6, 7, but only one of this zone is marked as a potential hydrocarbon bearing reservoir. Similarly, we detect the hydrocarbon potential using the quantitative evaluation, as I mentioned earlier. In this case, we have several source curves, and then over here you can see a new set of curves, which is the interpretation based on these source curves. And once these intermediate curves are predicted, then using signals in it, we predict quantitatively. We predict the hydrocarbon reservoir quantitatively over here. Okay, another way of detecting predicting hydrocarbon reservoir is about the thin bed evaluation using LRP, laminated sand analysis. And in this slide on the right bottom, this is a specialized way to determine LRP. And again, this is part of the quantitative evaluation. So this is about how we do the hydrocarbon detection using the conventional petrophysical workflows for quantitative as well as qualitative. Let's talk about how we do the same, achieve the same objective using the artificial intelligence approach. As we know that artificial intelligence is a system's ability to correctly interpret external data. It learns from the data and it apply the same learning to perform the same goal that usually is job of a human. And within artificial intelligence, a sub-branch, which is machine learning, is the study of the computer algorithms that improve automatically through the experience and using data. In this exercise, we are not going to develop a new machine learning algorithm. Instead, we are going to use various existing machine learning algorithms, and we used different parameters to determine the hydrocarbon, and then in doing that exercise, we find out the most accurate and fit for purpose machine learning algorithm that could solve the problem over here. So in this, we will infer hydrocarbon potential from the digitally well-logged data. The important part over here is that we already discussed the two set of well logs. One is the raw log, second is the intermediate. So our exercise was based on the raw log. So that's important to mention because the performance on the raw log was better than the performance on the interpreted logs. So the good thing is that in addition to determining the hydrocarbon flags, we were also able to classify that flags into different categories such as potential bypass, potential thin beds, oil and gas shows, and perforated intervals. So this is next to just the interpretation of the hydrocarbon. We were able to classify into different groups. Let's talk about the methodology, how we did it. So there are many ways in using machine learning. So we use the supervised learning technique, and then we use several algorithms such as decision tree, random forest, and neural network. But for this particular exercise, we use the results that we received from decision tree, as they were performing well among the other algorithms. And then we use a mix of technologies. We use TensorFlow, we use open libraries for deep learning, we use rapid miners, and very smaller tools which were not directly related to machine learning or AI. So that's kind of a data cleaning stuff and for that exercise. So the source data was comprised of 8 wells, and we split it into 2 parts. And then we take the first part, which is a bigger chunk, 5 wells, and we train our model using those 5 wells. And once the model is trained, we use the remaining 3 wells to predict the hydrocarbon. It means that the model was not having any exposure for the blind data till the model has been developed. So it's kind of a totally blind test. So in input curve, we have gamma ray, we have density, resistivity, and oil and gas shows. So here is the visual depiction of how our workflow works. We feed the raw data, and then we split into 2 parts, as I mentioned before. We train our model on the 70% data, and then we test the model on the remaining 30%, and we determine the model performance. If it is not enough, so we keep on changing the model parameters and achieve certain threshold, which is more than 90%. And then we engage subject matter experts to determine what is not interpreted correctly or which is not interpreted, and then we fine-tune the model until we reach to a conclusion that the model is good enough and it's trained enough and predicting correctly. Then we feed the raw data to the same model and we predict the hydrocarbon. This raw data mentioned in the blind test, pink color over here, when we feed this data to the model and we check the results. If the results are, we do the random check over here, and if the results are good, we publish it to the rest of the team to use. Otherwise, we go back to the fine tuning stage. So this is supervised learning. This is validated by subject matter expert, and this is, and later on it's applied to the blind data set. So another thing before we choose machine learning to help us to predict the hydrocarbon, we did some data analysis or data screening. So on the left hand side, you can see the multiple curves map against the same curves, and we can see the data distribution. And one thing you may notice that all these purple spots are clearly like there is clustered differently than the rest of the pink color bubbles. So and it's common across all the charts. So this gives an indication that the classification has a potential solution for this kind of a problem. And on the right hand side, we have two trees. This is the decision tree that system generated automatically, and you can see that the above one is 5-layer classification and lower one is 6-layer classification. So we perform this classification using multiple parameters and using more layers and lesser layer. But this is the optimum number of layers we reached, and it help us to achieve 90%. The 5-layer help us to achieve 90% accuracy. But obviously, rest of the one was not performing well. So it's not worth it to go into details of that. Let's see how our prediction worked. We fit the model with the blind data that we isolated in the beginning, 3 wells, and we are showing our result over here. Right hand side, we have the 1 well and its different logs, and on the extreme right side, we have second last column, which is the hydrocarbon detection done by the subject matter experts, and the right hand side, extreme last column, is the prediction done by the machine learning algorithm. So one thing you may notice that we didn't miss anything. All the prediction done by the SMEs are done by the algorithm as well. Similarly, this pink section is also interpreted, which means that the thin layer are also determined correctly in that right classification. And similarly, these thin but are very thin, like they are very narrow, but still they are predicted. So that's a good outcome of the first well. Let's look at the second well, and over here, similarly, the same logs over here. But one thing you may notice that these green arrows all here are the prediction done by the machine learning, is same as the done by manually. But you may notice that this yellow part, which is marked as the blue arrow, it is predicted in the machine learning, but it is not predicted by the SMEs. So it's not bad actually when the SME looked into details and they able to understand why it is predicted, and they may reject it or they may accept it. But the bottom line is that using the machine learning, you can analyze dozens and hundreds of well log very quickly without interpreting the middle stage curves, and then SMEs can go through it very quickly in a much faster manner, and they endorse it. The prediction has been done and used in the next stage of the business process. So this was the results, and in addition to this exercise by predicting the hydrocarbon using the well logs, our data science team has done several other achievements also. We are good at the geospatial data analysis. We do the data and wrangling. We do the grading and 3D visualization on the GIS surface and subsurface data. We also have an experience, several experience in natural language processing. Using this technology, we have successfully extracted well headers, reservoir properties from the petrographic reports, and reservoir results, lab results like RCA and SCAL analysis from the reports, and transform into a database. So our automation capabilities involve the data QC of the well and seismic. We automatically determine the poor and missing data in these data sets, and which reduce the data QC process significantly. Similarly, we also do the data classification and clustering in terms of PDF documents, their pages and pictures in it. So we can divide the data into different disciplines, domain, field, reservoir, and associate them to certain wells and geographic location. And the last but not least is our analytics and dashboard capabilities, where we do the decline curve analysis using the automated workflows, financial modeling on the field level, or the dashboards to consolidate information across the organization to produce a decision-making dashboards for the management. So that's all about the use of AI for hydrocarbon detection and our experience. And thank you very much for your time. Please go ahead and ask question and any comments on the this session. Thank you very much again.